In this video, we will discuss the background theory for a fairly general and computationally tractable class of short-rate models, the so-called affine term structure models. In the next video, we will investigate several examples of such models. Let's begin with the definition. A short-rate model is said to possess affine term structure, or ATS for short, if bond prices take the following form. Thus, the time little t price of the capital T bond depends only on capital T, which is just a parameter, and the variables t, time, and the short rate at time t. Here the functions a and b are just deterministic functions. So randomness enters into the bond price only via the randomness in the short rate. And a and b have to be sufficiently regular to allow us to perform the operations of differentiation that you are about to see. Here are some examples of affine term structure models. The Vasicek, CIR, Merton, Holy, and both Hull-White models are ATS models. But not all short-rate models are ATS models. For example, Dothan and Black-Karasinski are not. Now, the class of ATS models is quite well understood. They are those for which both the drift and the vol squared are affine functions of the short rate. Later, we shall also briefly discuss multi-factor affine term structure models, but we will not go into too much detail there. Note that because affine term structure models have bond prices that are given in the following form, and of course also in the following form, where y here is the yield of the T-bond, the zero coupon bond yield is an affine function of the short rate. The following theorem characterizes affine term structure models. A short rate model with risk-neutral dynamics of the following form, with drift mu and volatility sigma, is an affine term structure model if and only if mu and sigma squared are affine functions of R, i.e. if they take the following form, where the functions alpha, beta, gamma, delta are deterministic functions of T. We assume that mu and sigma are continuous and hence also that alpha, beta, gamma, delta are continuous. In that case, zero coupon bond prices can be expressed in the affine form shown. And moreover, the deterministic functions capital A and capital B can be determined by solving a weakly coupled system of ODEs. Here is the ordinary differential equation for B. This refers to the partial derivative of B with respect to the little t variable. We have a terminal condition, B capital T is equal to 0. And here is the ordinary differential equation for A, with a similar terminal condition. Notice that the ODE for B does not refer to A, and so can be solved directly. And that once we've solved for B, we can solve for A simply by integrating. Here we'll only prove one direction of this theorem, namely that if mu and sigma squared are affine functions of R, then the model is an affine term structure model. The other direction is not as important for us, and I will leave it to you to read on your own. For the proof of this theorem, suppose that we have a short rate model whose risk-neutral dynamics are of the form shown, and suppose further that zero coupon bond prices take the affine form. We take this expression for the bond price and substitute it into the term structure PDE. Recall that the term structure PDE looks as follows, where in this case the subscripts refer to partial derivatives with respect to the variable shown. In that case, we obtain the following equation, as you can verify yourself. Now, since this is equal to 0, we can dispense with the exponential here and simplify this slightly and obtain the following equation, which contains the partial derivative of A with respect to t as well as the partial derivative of B with respect to t. Moreover, since the terminal value of the bond is equal to 1, no matter what the value of R is, we must have that both A and B are equal to 0 at the terminal time. Suppose now that the drift and volatility of the short rate can be expressed in affine form, i.e. as affine functions of R, as shown. Here note that it's the volatility squared that is an affine function of R. Recall that alpha, beta, gamma and delta are just continuous deterministic functions of t. If we plug that into the equation that we derived at the bottom of the previous slide, namely, then we obtain the following equation, where we have grouped all the terms containing the short rate on the right and all the terms not involving the short rate on the left. Now notice that if the short rate changes, then the right-hand side will change, but the left-hand side will not. This is actually impossible unless both sides are identically equal to 0. In that case, the expression in the square brackets on the right is the ODE for B, and the expression in the square brackets on the left gives us the ODE for A. We can then solve this weakly coupled system of ODEs to determine the functions A and B directly. Note that the ODE for B, a Riccati equation, does not contain A and can therefore be solved directly, usually numerically. To solve for A, we use the fundamental theorem of calculus, which says that the integral of the derivative is equal to the function evaluated at the endpoints of the integral, noting that A capital T is equal to 0. And hence, once we've solved for B, we can solve for A simply by integration. The proof of the reverse direction is on the next 2 slides and is left to you to read.